Good afternoon, students. Today we will be starting with collision theory of chemical reactions. Now, collision theory is actually not a very new topic. We have some idea about collision theory from the kinetic theory of gases. So, from there, we can take the concept and we can proceed with collision theory. Now, what the collision theory says? Collision theory says that the reacting species or the reactants taking part in a chemical reaction can give product only in case they come in contact with each other. That means they will give rise to products only they will collide with each other. That means reactant molecules are going to collide and that is going to generate the products. So this is known as collision theory of reaction rates. So this is specified as collision theory of reaction rates, right? Now, let us further proceed with this. Now, according to this collision theory of reaction rates, the basic condition for a chemical reaction is collision among the reactant molecules or collision among the reactant species. Now, here we come across a term which is known as collision frequency. Okay. Now, collision frequency is specified by the letter Z. What it states? Collision frequency means we can make out it's a number. So, collision frequency is nothing but the number of collisions that take place per second per unit volume. Per unit volume of what? Of the reaction mixture. So this is nothing but collision frequency. Okay. Now, if we consider the reactant molecules, whenever we are starting with a reaction, we have a large number of reacting species. Means large number means reacting species of a definite kind or two or more kinds, but each species is present in large numbers. Okay. Now, the collisions actually, they are taking place at a very high rate, and in general, the value of this collision frequency is very high. Now, for some reactions, the collision frequency is so high that the reactions are very fast, or we can say the reactions are extremely fast, or we can say the reactions are instantaneous. But there are many reactions which are quite slow. Why the reactions are quite slow? This is because of the collision frequency. Now what happens? The reactions are slow means we need to give something to trigger the reactions. That means the reactions are not going to proceed under normal conditions. That means it is not necessary that all collisions lead to products. Okay. If we consider, suppose in a certain reaction consisting of a certain number of certain kinds of reacting species, suppose 100 collisions are taking place in a second. So, what value I have stated here, that's a very low value. Let us suppose. Now, all the collisions are not giving rise to product. Now, suppose only 40 collisions are giving rise to product. So, out of the total number of collisions which are taking place, how much are giving rise to products? Only 40%. So, 40% are only successful, and the rest collisions are not going to fetch anything. That means with whatever energy those collisions are taking place, those are wasted. So, out of the total number of collisions, those collisions which gives rise to products, they are known as effective collisions. And effective collisions are nothing but a fraction of the total number of collisions. All the collisions are not going to generate product. Okay. Now, what is important for us is that means if we want to go for a reaction which will give a very good yield where energy loss will be minimum, we need to seek for the conditions which will result in greater number of effective collisions. That is our motive. Now for that very reason, we need to see that in order to make collision frequency means number of effective collisions very high, what are the requisite parameters we need to take into consideration? And if we keep a notice on those things, those parameters, then we can go for maximum extent of effective collisions. So from here, we need to keep two things in mind. That means in order to make collisions more effective, the reacting species have to overcome certain obstructions, and those obstructions are termed as barriers. Now, which are the two barriers which have to be nicely overcome? One is the energy barrier, and the other one is the orientation barrier. Okay, so these are the two important barriers which the reacting molecules or reacting species must overcome, and then only they can easily generate the products. Now what about energy barrier? In order to make the collisions fruitful, or in order to make the collisions effective, the species taking part in a chemical reaction must have a certain minimum value of energy. What is that minimum value of energy? The minimum value of energy is termed as the threshold energy. This must be there. Okay. The threshold energy must be there. Threshold energy is actually the energy needed to break the bonds in the reacting species. If the bonds in reactants are not going to break, then we are certainly not going to get the products. Why? What is a chemical reaction? A chemical reaction is nothing but a process of breaking and making of bonds. Bonds in reactants are broken and new bonds in products are formed. Until and unless the bonds in reactants are broken, we are not going to get any product. No new bond formation will be there. So this is threshold energy, means the energy which is required in order to break the bonds in the reacting species. Now let us suppose a situation like this, that the energy of the colliding molecules, they are having some energy, but the energy is less than the threshold value, then that collision is wasted. That's not going to generate any product. Okay, so we must keep in mind that the energy which we are providing must at least be equal to the threshold energy. Otherwise, if two molecules are approaching, one is approaching towards the other, this is one molecule, this is the other one. Okay, if this is approaching towards this, okay, so they are approaching with some energy. But if that value of energy is not at least equal to threshold energy, it is less than threshold energy, then that energy is wasted because that's not going to generate anything. Okay, so the key term is threshold energy. The other thing, another factor which is also very important, that is orientation barrier. Okay, now this is very important. Why? Because if the reacting species are not properly oriented, then we are not going to get the products. Okay, now let us suppose a reaction like this. AB is reacting with CD, giving rise to AC plus BD. So A and B are the reactants and C and D are the products. Okay, now suppose AB is like this and CD is like this, right? So what will happen? What is the result? We are going to get something like this, AC and BD. Okay, now if AB and CD are aligned like this, we are going to get, because the existing these bonds will break and new bonds will be formed. So we will see the intermediate something like this. It's not intermediate also. Let us suppose it as a transition state. It will be looking something like this. The bond between A and B and C and D, the existing bonds are going to break and new bonds are going to get formed. Okay. So after a certain span, A will be totally having a disoverlap with B, similarly C with D, and new overlap will be there between A and C and between B and D. But if we are not having the alignment like this, but rather we are having the alignment like this. AB is there and CD is present like this. Okay, so have a look. Here D is at the closest approach distance with A. So we don't want a bond between A and D, and we don't want a bond between B and C. So if this kind of an orientation is there, that is totally wrong. This is not going to fetch the products. Okay, so two factors are important. One is energy factor, the other one is orientation factor. But one thing has to be mentioned, that the energy factor is much more significant than the orientation factor. The reacting molecules having proper orientation will not form products if they don't have the energy which is at least equal to threshold energy. You are making proper orientations, but they don't have the energy. After proper orientation also they are colliding, but that energy of collision is less than the threshold value, so we are not going to get the products. Okay, now let us have a look at the mathematics of this. Now we all know that rate of reaction can be expressed as dx by dt. Okay. Now, rate of reaction is directly proportional to the collision frequency. But what is important is not the number of collisions, but the number of effective collisions. So more than collision frequency, effective collision frequency must be taken into consideration. So if Z represents the total collision frequency and F represents the fraction of molecules which represents effective collisions or which are undergoing effective collisions, so rate of reactions is equal to Z into F. Now, from kinetic theory of gases, it has been found that F is equal to exponential minus EA by RT. Okay, so EA here represents activation energy, R is the universal gas constant, T is the temperature. Now what is the significance of this? That we will discuss later. But now we should take this into consideration, that the fraction of total molecules which are undergoing effective collisions, that is equal to exponential minus EA by RT. So rate of reaction which is equal to Z into F can be written as Z into exponential minus EA by RT. Right? Now we already know that rate of a reaction is directly proportional to rate constant. If the value of rate constant will increase, the rate will automatically increase. So in place of rate, we can write rate constant K is equal to Z exponential minus EA by RT. Right? Now, here too we have taken into consideration the energy factor because we have EA here. Okay. Now let us consider now EA is equal to the threshold energy only. But there is some difference between threshold energy and activation energy. But now let us consider EA as something equal to threshold only. Okay. Now, so energy factor has been considered, but we did not take into account another factor, which is also an important factor, that is orientation factor. So, considering orientation factor, this form gets modified to P into Z exponential minus EA by RT. What is the significance of P here? P is nothing but it is defined as the orientation factor. P is the orientation factor. So ultimately the rate constant can be expressed as P into Z exponential minus EA by RT. Okay, that's all for today.